Hello, my name is Tori Catlett, and my presentation is about radiation teratogenesis. I would first like to introduce the topic to you. Teratogens, as defined by Gilbert and Baresi, are exogenous agents that cause disruptions in development, resulting in the formation of congenital defects. The beginning of development is crucial for any organism, as we have observed with the vernalization in Arabidopsis, all the way to the necessity of both Ra and FGF present in limb bud development. The picture on the bottom left is Arabidopsis daydreaming of its previous snowy days, and the picture on the right is of a limb bud developing with the antagonistic relationship. Human development is divided into two sections, as observed in this diagram. Weeks 1 through 2 are the embryonic period, and weeks 3 through 38 are the fetal period. If a teratogen is introduced at any point during development, there is a risk of the offspring having a birth defect. But if a malformation arises during the embryonic period, the embryo will be aborted by the body, with the mother likely not knowing she was pregnant. Teratogens cause birth defects by altering the early developmental processes and patterns, but the mechanisms by which these effects arise are still largely unknown. The teratogen I will be discussing is ionizing and non-ionizing radiation. Ionizing radiation includes cosmic, gamma, and X-rays. Non-ionizing radiation is ultraviolet light, visible light, infrared, microwaves, and radio waves. Ionizing radiation can cause birth defects such as decreased brain development, reduction in height, severe mental retardation, and limb deformities. These birth defects have been observed in offspring from mothers exposed from both medical and non-medical radiation. The picture on the bottom right is of a child who was born with congenital defects secondary to his mother being exposed to radiation from the Chernobyl accident. We're exposed to radiation daily. Understanding which stages of pregnancy and what doses of radiation are toxic to development is crucial in preventing birth defects caused by radiation in future populations. The image on the bottom elicits what potential defects could occur when a potential carcinogen is introduced to the embryo or fetus. With this, we are still uncertain what levels of radiation are required to cause these effects. The image on the right shows the relative doses from radiation sources. Interesting enough, Denver is on the list as living at high elevation with an exposure of 0.8 millisieverts. Millisieverts is the radio protection unit. Now we are going to move into biology and results. Radiation causes birth defects by disrupting the development of the neural plate, and it is during neuralization that the eye is developed. Following the Chernobyl disaster, congenital anomalies were observed in offspring of mothers who were exposed to cesium-137. These children had microphthalmos, which is abnormally small eyes, anophthalmos, which is where both the globe and ocular tissue are missing from the orbit, as well as axanocephaly, which is where the brain is located outside of the skull. Cranian et al. Conducted an experiment by irradiating the heads of developing mice fetuses. Then they were snap frozen, and the RNA was quantified. They found that irradiation in the form of X-rays during neurulation leads to differential expression of key developmental genes such as PAX6 and LHX2. Disrupting gene expression causes birth defects in mice, which they believe is parallel to us. Detailed information on the mechanisms of human embryonic brain development sensitivity to ionizing radiation is not present. Wollinger et al. Knew they could use human embryonic stem cells and their development to neural lineages as a model for embryonic brain development. To assess the effective exposure to low and high doses of radiation on gene expression during development, transcriptomes were assessed using RNA sequencing during neural differentiation at 3 time points in control and irradiated samples. The first time point was when the cells were still pluripotent, day 0. The second time point was during the stage of embryoid body formation, day 6, and the third and final time point was during the stage of neural rosette formation, day 10. Overall, low-dose irradiation did not result in changes in gene expression. High-dose irradiation resulted in downregulation of neural differentiation, markers on day 6 and day 10, resulting in mutations of the neural lineage tissue. Now we will move on to relevancy. Teratogens are a public health issue as what individuals are exposed to not only affects us, but upcoming generations as well. As our possible exposure to radiation increases due to medical diagnostic techniques, increased air travel, and increased cellular use, the need for funding in radiation teratogenesis research increases as well. Increased understanding of the mechanisms by which congenital defects arise from radiation exposure will allow us to have more accurate guidelines for radiation exposure in developing humans. This research surpasses fetuses because better understanding risks of infertility and creating guidelines for all individuals is crucial as our exposure to radiation increases. The image on the right shows the average doses for a worker in each corresponding field. Now we will move on to future directions. Moving forward, we need to understand if non-ionizing radiation is capable of causing congenital abnormalities. We know and believe that non-ionizing radiation is not dangerous to us, but there has been limited research on the effects of non-ionizing radiation in early development. Last is works cited. Here's all of my citations listed in order of appearance. Thank you for your time, and I hope you enjoyed my presentation.